Hello, my name is Shay and this is the System Acceptance Review for the Rose-Hulman rover team. We represent Rose-Hulman Institute of Technology in Terre Haute, Indiana. We have about 15 members on the team who are split into two sub-teams. The first is the mechanical team and the second is the electronics or controls team. The mechanical team designs solutions for the physical problems presented by this challenge and fabricate parts for the rover. The electrical team handles the software and electronics that go into the rover. The two sub-teams meet independently during the week to work on their individual projects, then come together for a full team meeting at the end of the week to discuss and integrate their work.
The main design philosophy behind the mechanical team was to keep the design choices simple and stick with concepts that were well proven and that we know we could work well with. To this end, the robot chassis is largely recycled from previous designs built at Rose-Hulman and uses aluminum tubing left over from a previous robot. These choices have made modifying the chassis relatively simple to the point where we could easily invert the entire chassis and still run it normally. For our drivetrain, we chose to go with the rocker bogie design with the passive differential gearbox to account for twisting. While this design might be mechanically complex, it limits the need for damping systems that we are not experienced with. For our arm, we chose to simplify the initial construction and final controls for the operator. To do this, we used linear actuators on the base of the arm due to the ease at which we could move them around and modify the torque output by the arm, and a spherical wrist. The spherical wrist is a great asset for controls planning as it allows us to simplify the inverse kinematics and pre-program pathways that a robot operator would otherwise have trouble with, such as rotating a crank.
Our rover's main computer is a Raspberry Pi 3 running Ubuntu. We control the rover from a base station laptop that connects wirelessly to the rover via off-the-shelf Ubiquiti Networks routers. The Pi collects input from onboard sensors in the base station to control the rover's actuators. The rover is powered by a single 12-volt lead-acid battery. It supplies ample power to the motors and actuators of the rover through the power distribution panel. Attached to the power distribution panel is the voltage regulation module. It supplies limited 2-amp power to the more sensitive electrical components of the rover. The voltage regulation module provides 5 volts to the Raspberry Pi and 12 volts to the power over Ethernet injector used to power the onboard router and antenna. We use 4 Victor SPX motor controllers to control all 6 of the drivetrain motors on the rover. Each motor is controlled by a PWM signal. To create a PWM signal, we output an analog voltage from our Raspberry Pi to an analog to PWM converter. The linear actuators for the arm of the rover are controlled by applying 0, 12 volts, or negative 12 volts for stillness, extension, or retraction. For each actuator, we use 2 electrical relays with reverse polarity to achieve the possibility of negative polarity on the actuator. Our team utilizes ROS to control the software on the rover. ROS allows us to organize our robot's code into several small nodes, whose outputs are only called upon when needed. This keeps our code organized and allows us to work in parallel to program different nodes. Using ROS, we are able to call a Python script that automatically sets up a network connection between our rover and our base station, provided our base station is also running the necessary script. Once a connection is established, we can remotely access the Raspberry Pi from the base station. More importantly, we can send and receive messages back and forth between the two routers, allowing us to produce messages in the appropriate ROS node. We can use the connection established between the rover and the base station to transmit messages to the rover. At the base station, we can run a Python script that reads user input from an Xbox 360 controller. The script puts the input data into a string, which is set to the Raspberry Pi. The Raspberry Pi then parses the string into data that represents the state of the controller. It broadcasts this data to a ROS node where it can be read and acted upon appropriately. For example, here the left joystick on the Xbox controller moves the left wheels of the rover with a speed proportional to the value of the joystick. The rover is able to determine its current location at any time using the USB GPS on board the rover. We have written a Python script that reads data from the USB port as a comma-delimited string and then parses it into useful data. We have verified that the coordinates produced match the rover's location within a few meters. We are also able to transmit live video wirelessly from the Raspberry Pi to the base station using USB camera. We can run a Python script on the Raspberry Pi that sets up the stream using the socket interface. This video stream will provide visual feedback to the operator during the competition.